Hi, happy holidays. I'm Richard Tesmer, and I'm here today to discuss with you process integration projects, mostly from the point of view of geophysics. So, first off, in ways of an introduction, my partner and I are avid foster failures. That means a foster might come to stay with us, but they never go anywhere else. Once we have an animal with us like that, we never vacation or travel without them. The last one to leave us for the Rainbow Bridge was with us for 21 years. My partner and I have been together for 24 years. I am a lifelong member of the PMI Houston chapter and the DC chapter. And a little unknown fact, the Houston chapter was the original PMI chapter, and we just got done celebrating our 50th anniversary this last summer. I do have my certification from PMI as a PMP. I am also certified in SAFE, Agile Fundamentals. I have my bachelor's degree in business and project management from AIU, and I'm completing here shortly my master's degree from USC in project management. So, with that introduction, let's jump right in to the approach to integrated geophysics. So, again, we really have four different areas we're going to focus on. First, we're going to focus on resource exploration. Um, Mapping out those resources, whether it be oil beds in the ocean areas or mines in different parts of the world, whatever needs to be mapped. We have to assess the value of that mapping and what information does it return. Is it going to be a good source to drill or not? And then what's going to be the impact of that work on the ecology? If it's really going to be really negative, is it still such a good idea to do it? That's all about that resource exploration. Next, we want to talk about looking at infrastructure development. Just like any other infrastructure project, there's different things that we always have to keep in mind and work towards. So first off, we're usually going to be using civil engineering as our most common model when we're doing integrated geophysics. There are going to be some critical conditions because sometimes this equipment is really dispersed in geographically challenging areas of the world. Um, and then once we get the data back, are we going to be able to take advantage of these supercomputers? Or what about the cloud? It's all about the infrastructure and how we're going to use it. Environmental assessment. Again, what's the impact of these different sources being drilled or whatever it might be happening with them? So we need to take a look at it from the point of view, what kind of contamination are we causing with the resources and the explorations? Are they just geological hazards that we're creating? And then again, can we put in place a remediation plan or recommendations for a remediation plan so that the folks that are using this data can be more responsible citizens of the world? And then lastly, seismic monitoring. Very obviously, it's very important, very critical. It's all about monitoring that information and then taking that model and creating from enough data points a predictive way of knowing when these earthquakes or seismic events are going to occur. If we can do that, our communities could be much better at preparation. We would have a lot less property damage and loss of life. Now, as we move from there, let's really talk for just a moment about that geological network. What is it made up of? Well, first off, it starts up there with space. You may not realize it, but we have satellites. They're always mapping things from outer space, looking at the upper levels of the atmosphere, what damage are we causing to them with the disbursement of chemicals, etc. That's followed by the surface areas. Now, there's a lot of different equipment as you can see on there, monitoring all different parts of the surface area, and then that's going to be followed by the subsurface area. And then we're really talking about water and magma volcanoes. So that's our three primary geological network areas that we're looking at. Now, as we integrate the geophysical methods, there's certain things that are very important, like any other project. Research infrastructures obviously play a really important role in the resolutions of coming up with how to deal with some of these different problems. Likewise, climate change is real, and we can continue to study that by combining GIS data with sensing, geoelectrical methods, groundwater, all the different efficiencies of cost can be combined into a data fusion, making it much easier for us to deal with that data. Now, there are integrated methods that can reduce the overall cost of some of these explorations. We can minimize the number of surveys that have to be done, or even optimizing resources. There's different things that can be more cost efficient. There are ongoing analysis, temporal monitoring of geophysical changes over time. So different insights can be gathered there as we create these predictive models. And then interdisciplinary collaboration. That's really, no matter what scientific discipline you're in, we should be able to work together on this data and come up with holistic reviews of what it really means to all of us, not just keeping that data in our silo. And then as we identify potential hazards, it's all about risk management. So what is the risk mitigation plan for anything that we've been able to identify? Now, integration starts with combining the seismic, magnetic, and other geophysical methods. So we're going to start off with data acquisition. That's the integration of data from all these multiple sources: sky, surface, subsurface. We want to be able to process that data. So we're going to want to use data transformation services so the data becomes more homogeneous. We want to use machine learning, artificial intelligence, so we can process this data much faster than before. We want to be able to take that data and interpret it. And again, going back to that machine learning might be a really good way of speeding up the process of interpreting all this gigabytes and trillions of gigabytes of data. We want to make sure that we have integrated analysis of that data. So again, now it's all been transformed into one holistic view. What can we look at it together to integrate it? And once we're integrating it, how are we reporting it? We need consistent, transparent reports that people can rely on over and over and over again for good insights and recommendations. And then how are we going to disseminate that information? In today's world, cloud-based systems, always on, always now, always anywhere, always by any person, makes it very easy to disseminate what used to be complicated information. As we move beyond that, and we're looking at now geological integration, kind of about that reporting, requirements planning. We've got what is our data systems, what's our agreed upon machine learning and the functions and the algorithms. And once we start doing all of this and we're looking at output, what does the output look like in these interactive 3D models? So again, back to the integrated system, the data management from space, surface, and subsurface, and all these different sources for each of those three. How do they move together in order to be homogeneous by the end as they go through that data transformation service? It's a very important part of it that must be worked on at all times. Just like any application, there are three layers that are very common, and security plays something in all three of those layers. Now, the data is the bulk of all of the data that's being collected and stored somewhere, most likely these days on supercomputers or in really just distributed cloud-based systems. The bulk of the data will sit there, and only a smaller subset of that data is what's being made available to the public. Now, there is an application layer in there, and that's where we do keep talking about the logic and the machine learning and artificial intelligence. We don't want the machine getting carried away and running off to other parts of the world with our data. So again, security is an important part. Then there's those user interfaces. That's the creation of all of these interactive data models and making available what's really useful and what's not, archiving it. So now as we take a look from a project management office, my favorite area, what is the PMO plan? When we're looking at data management, we know that we have this raw data we keep talking about, the data transformation services, but what about the data archives? What needs to be archived for how long? That's important because data storage isn't always free. So you got to think about that in advance. From an education point of view, if we do use artificial intelligence, can we put that into a positive spin, making sure that as we create these cloud-based reporting systems to disseminate that information, that everyone understands the machine learning model? Now, availability. Raw data should always remain locked only to the actual researchers themselves. It needs to be available 24/7. We need to have hot and cold disaster recovery backups so that when something goes down, we're back up as quickly as possible. And of course, again, that security model. Now, as we're optimizing the collection of geophysical data, again, we're really looking at three different areas, 6 different areas. So first off, what about the quality of the data? If the data is not good, that means at the collection point, then it's not going to do us any good further down the road. So that means field training. Make sure that everyone in the field that's collecting data not only has the right equipment for it, but also knows what they're collecting, how that's going to be used, so they can make sure they're collecting the right data as quickly as possible. Now, once data is being collected and analyzed and report, what techniques are going to come into play as we look at the selection of data? And data integration, to get back to those 3 layers, also the 3 different sources. How do we integrate all that into a homogeneous model? Because again, we have all this equipment around the world, above the world, under the world. So how do we keep all of that calibrated so the data that it's collecting is proper, appropriate, and useful? And then project planning. If you're going to do global work, you have to have projects planned out to take all of this into account. Now, project management in integrated geophysics is not that dissimilar from any other project. You have to start off by being able to define your objectives and your goals. Once you can plan for your geophysical projects, then you want to make sure you identify your resources. That's your personnel, your equipment, the actual technology that you're going to use to get all these resources. You have to be able to execute on that plan. All about how you conduct those surveys, collect the data, and communicate it. And of course, just like any other project, you've got to monitor as you go along. Check those milestones, your sprints, your gates, your insights and conclusions. And then you need to be ready to analyze. You have to interpret your data. You have to be able to report on that data. And then at the end, during a collaborative model across these cross functions, make sure you're doing lessons learned. What could you do better on the next cycle? So again, very similar to a regular project model. When you're trying to be successful, though, with geophysical models and projects, it's important to keep in mind how regular are the updates? Are they prepared for open and acceptable feedback loops from all of our stakeholders? Is there clearly defined OKRs, those objectives for your organization that everyone needs to know that's what we're trying to achieve? One of the important things you want to take a look at is these organizations, their motto should be, we provide advice just when your business needs and just when you ask for it. If you think about it, that's the JIT model, just in time. Now, technology is always going to have some sort of a role with integrated geophysics. First off, the equipment. That's your data acquisition. It might be something as simple as handheld, tripods, bigger, up in space like satellites or underwater. So there's all sorts of different things you need to think about how you're going to collect your data. Once you collect that data, how's it going to be processed? Are you going to use something like the U.S. Geological Service and its massive supercomputers, along with cloud-based computing, machine learning, and artificial intelligence to speed up distribution? And then what kind of visualization tools will you use? Because it's important that those 3D models are interactive. It makes it easier to learn, it makes it easier to format them and collaborate and make better data decisions. Now, the use of machine learning, first off, we're talking about predictive modeling. It's all about helping create a better predictive model, like for seismic activity, as one example. Um, so we don't need to be afraid of machine learning. We just need to make sure that it's set up correctly and securely. Some of that comes along with data classification. Different organizations can use different data in different ways. So it's a matter of making sure that it's all set up in a secure model and constantly being monitored. In addition to that, when you're looking at the seismic data in particular, organizations can use these data fusion tools. And we're really talking about health monitoring. Where is our seismic layers the healthiest and where are they the least healthy so that they can determine that there's a higher risk of a seismic activity about to occur. And again, going back to the project management office, management principles apply here just like they do anywhere else in any other project. In geophysics, we're starting off with stakeholder engagement. We got to make sure they're all identified. We know who they are, what they're responsible for. We've given them the requirements. In project lingo, that's a RACI chart. Do the same thing here. Risk management, again, it's all about identifying as many of the known unknowns as you can, coming up with mitigation plans for those, and coming up reserves for the unknown unknowns that you couldn't prepare for at all. Now, there's resource allocation. As you're setting up your budget, you want to make sure you're looking at personnel, equipment, and your funding, because all three things have to be balanced. And then you have to have that clear communication plan. Who gets what information and when and how often? Now, all of this together forms the project plan. So that helps you create your work breakdown structure, where you get a detailed project timeline. Or if you're doing agile, maybe user stories. You might create phases or gates or sprints for your geophysical project work. You need to consider whether you can go with waterfall or agile or scrum fall. Which one's going to make you the most adaptable to changes should they occur? Now back to that PMO again. I like that PMO model. How do we create these clear objectives and project timelines? First off, we have to define our goals. No surprise there. They need to be about that integrated geophysics and what we are trying to achieve. Secondly, we need to make sure that we know how we're going to conduct the research. What are we going to do to investigate the latest technology available or techniques that others are already utilizing that we can apply to our own research or our teams? We need to develop really concise plans, very detailed work breakdown structures and project plans. Um, we need to make sure that we know how we're going to implement all of this strategy. We need to be all on the same plan. How are we going to execute the plan? How are we going to ensure communications and collaboration amongst everyone? And then at the end, how are we going to review the outcome of all of this data? Kind of think of it as lessons learned. Your KPIs. How many of your KPIs did you actually reach in your goals? And if you failed to, why? And how can we do better next time? So the PMO, when we're looking at project budgeting for integrated geophysics, no different than any other project. We may have different cups that the budget is going to tap into, and we need to determine how much each of those is going to get of the total budget. So the first one's going to be like the implementation. What percentage of this budget is it going to take out? And you have a detailed budget tracking system to make sure that your earned value is being traced all the way through the project. The second budget or track might be your project updates. What percentage of the budget is going to be reserved for doing EVM calculations to track the work and how it's going to be reported? Third, what about the variances themselves? Those known unknowns. You need some sort of reserve account so that either management or the project contingency funds are there to be used when something arises that wasn't originally planned for. And then lastly, forecasting. You got to be prepared again for those known unknowns, and you got to be ready for shift happening. Shift matters. It happens all the time. Be prepared for shift. Now, the next one I want to talk about real briefly is the golden triangle of project management. You'll also hear it referred to as the triple constraints. So it has three sides to the triangle: time, cost, and features and functions. The middle of the triangle is quality. If your triangle is in perfect balance as an isosceles triangle, all three sides equal each other, quality is almost guaranteed to be high. However, if at any point you change one of the three sides, like maybe you make functions longer, it's going to impact time. You have less time to work on it, and it might cost you more as well. And quality will definitely not be as good. So, however you change your triangle, it's important to keep it in balance. You can't have any one side taking over the others. Now, let's go into risk management. Uh, First off, talk about the quality of the data. How is it being collected, disseminated, analyzed? How is it being communication between all the different teams? How often? To whom? Uh, what about regulatory? The European countries have a lot more regulations about some of these areas than we do here in the U.S. So you have to be aware of, especially if you're a global association, of all these different regulatory bodies and follow them. And then, of course, money. You've got to make sure that you understand that the budgets are realistic and that the requirements have to be trimmed if the budget is too tight. So again, regular project management concepts. Now, there are always technological advances with integrated geophysics. Things are changing all the time between hardware, integrated 3D modeling, how we think about things, whether you're a machine or a human. All of that's always occurring. 3D imaging, real-time monitoring, and mobile technologies out in the field. Now, we also want to talk about workflows. How can we streamline workflows in these geophysical integration projects? So the first area is we've got to make sure, again, just like always, it's all about that identifying those goals. What is our KPIs, our OKRs? What are we looking for? And then how are our resources going to be allocated to streamlining it, making sure that we're not overworking some folks, underworking others. And then how do we outline the steps to get to our goals, like the WBS? Assigning people responsible to those to where it's very clearly defined where they begin, where they end, and what the expectations are. In particular, timelines. You want to make sure those are set and that everyone understands their deliverable is due by that time. If you come in sooner, it really should not come in later. And of course, we need to review the outcomes. How well did everybody perform? And then lastly, we want to talk about the applications of integrated geophysics. So there are different ways where this type of stuff is occurring in today's world. Some of it's with oil exploration out in the water. Some of it might be these strip mining places where it's about minerals. We're prospecting the best places to mine for minerals. And then groundwater studies, looking at those geophysical techniques to look for better management of our water resources. And then lastly, what about the environment? That's assessing those subsurface contamination that's occurring from any of these three areas and coming up with mitigation programs to keep all of that in check. From a PMO perspective, when we're looking for enhanced outcomes with integrated geophysics, again, we're talking about those resource allocations, risk mitigation as a policy, how we're going to communicate with each other and break down those silos, and how we're going to measure our performance, KPIs and OKRs. Now, the PMO also has to work with the stakeholders, the project sponsors or C-level executives to come up with an agreement of how important everything is within the project. So, when we're first looking at project management itself, there's different areas. So when we look at the PM model, there's cost efficiency. How important is that? Or is resources more important? If so, we need to determine how much of that percentage. Everything has to equal 100% for each of these buckets. And then lastly, what about risk mitigation? How important? What is your risk tolerance? If it's too high or too low, you're going to be impacted. So again, this all has to be balanced in the project management model. Now, when we come to the second model, we're talking about actually achieving objectives. So first, we're really talking about accuracy of the data. I would think that's going to be pretty important, how accurate the data is itself. After data accuracy, we want to talk about that with regulatory compliance, like we were mentioning earlier, with what part of the world are you in, and which country you're dealing with, and what are the different rules. How important is that to are we willing to overlook the models, or do we have to follow them? And then last area is going to be our the community usage of the data. How important is it to create these collaborative models, these interactive 3D models that everyone can use? So when we're talking about cross-disciplinary insights, breaking down those silos, how important is that? Or can everybody just keep their data to themselves? Probably shouldn't, but again, how important is that in the project? Now, the next area you want to look at is, what about the public perception? How much do we care that they think about how we collect our data, how we analyze and report it, and how we disseminate that data? However important that might be to us as an organization. And then the last area is going to be that innovation advancement. That kind of ties into that public perception. How on top of innovations are we remaining so that we're always using the best and the most advanced tools possible? So again, what's its overall importance within the project? Now, after that, you might be asking, Richard, how do we organize a PMO office? Well, there's no set rules of what you have to have, but I do like to kind of break it up into like 3 areas when we're talking about geophysics. So, and the first area is really about the project managers themselves. The second area is kind of like the data services, from collection through the data transformations, and then whether we're using artificial intelligence, machine learning, etc., and archiving, all follows under data services. It's probably too big of a job for one person. You probably need to break it up into at least 4 people. And then the other area, the last one, is programming leads. Now, sometimes programmers are a whole separate team or department, and that's fine, but there still needs to be a definite, strong integration with the PMO to make sure we're all getting the same targets. And you notice I have 2 of them in a couple different colors there because they're actually going to come into play with all sorts of other parts of these departments. Auditors who are doing peer reviews and helping look at artificial intelligence, measuring whether or not it's doing what we wanted it to do, and doing that the QA and UAT teams, and of course looking at those cloud-based services. So my thoughts as a PMO, as a director of a PMO, on the future of integrated geophysics models is really simple. The whole is always greater than the sum of the parts. Think about that for a moment. The whole is always greater than the sum of its parts. So I guess if you want to think about it a different way, it might be look at the big picture, don't get caught up with the trees in the forest. I think that's a great way of looking at that. I have a few other thoughts I'd like to close with. There's some big thinkers that were out there in the world of ecological and geophysics. One of the first ones is Louis Pasteur, not a new figure, kind of an older one. He was known for saying, in science, there are no shortcuts to the truth. That goes back to that transparency. You don't want to be putting out falsehoods or half-truths. It needs to be the entire truth. And then the next guy is Bill Bryson. Now, he once said that energy is liberated matter. And matter is energy waiting to happen. So think about that, especially when you're looking at volcanoes and earthquakes and all these other disasters. How does energy and matter play in there? What is the relationship? Now, the last one here is, don't really know who said it, but it's a great quote. In geophysical projects, Integration is not just a method, it's a philosophy. It drives us to see the unseen and understand the unknown. Let that sink in for a moment. I do want to thank you. Again, I'm Richard Tesmer. I hope you found this enjoyable and informative. And a couple of quick pictures here. Mentioned to you earlier, I have all these dogs. Here was 3 of the Italian Greyhounds. That one in the very bottom there, she's the one who was with us for 21 years. This was one of my original ones, passed away many years ago. This is one of the ones we have right now, definite foster failure. And this is them enjoying sitting on the sofa under the Christmas tree. This was another foster failure. She was supposed to have been an Italian Greyhound. Obviously, she wasn't. She came to us and was with us only for a very short period of time. And this was that one that lived for 21 years. Her name is Mia. And then, yes, she looks a little feisty because she was. Oops, sorry about that. This is our latest failure. His name is Lucky. We rescued him right off the streets and saved his life from being hit by other cars. So again, I do want to thank you. Hope you enjoyed those little pictures right there.